Hello everyone. In this example, we're going to use AI and machine learning, specifically K-NearestNeighbor algorithm or K-NearestNeighbor, a classification model to predict whether a signal coming via a telescope is indicative of a pulsar being detected or the radio waves collected are only a cosmic noise and not truly a beam emitted by a pulsar. We're going to use a data set having past historical data collected from telescopes for different parameters used to see whether a pulsar candidate happens to actually be a pulsar or not. But at first, what is a pulsar? So, pulsars emit light beams due to the rotation of a highly magnetized neutron star, where its magnetic field accelerates charged particles and causes the emission of electromagnetic radiation. In electrical communications, the change of a magnetic field around a conductor, which would be a metal wire, would cause an electrical current being created. But the opposite is true as well. If you have an electronic or electrical current passing through a wire, it would create an electromagnetic wave, which is what we call a radio wave, given its lower frequency. But at much higher frequencies, electromagnetic waves are visible. They become visible and what we call light waves. According to Wikipedia, a pulsar is a highly magnetized rotating neutron star that emits beams of electromagnetic radiation out of its magnetic poles. Now, imagine a current going through a conductor. Just like these charged particles we've spoken about are going through a circuit caused by the rotation of the neutron star in a circle around the center of the neutron star. So if we get a section of that circuit or a fraction of that circuit, and let's say the direction of the current is the same as the direction of the charged particles. It is the same analogy, by the way. So the magnetic field would be looking something like this. A force rotating around the conductor or around the charged particles we've spoken about in the pulsar case. Those magnetic field rings would be rotating clockwise to the direction of the current, which is, by the way, the law of bolt or screwdriver heading. If you can imagine a bolt and a screwdriver fastening the bolt from left to right into a wall, it would be rotating clockwise, the same direction of a clock. And that would be the direction of those magnetic fields. The same way for a pulsar, for which the charged particles are rotating around a ring, and the magnetic field would be also going clockwise based on the direction of these charged particles. And it would concentrate in the middle. That's why you would have a pulsation of beams of light from the upward and downward normal direction of the pulsar. Now, the rapid circular movement of charged particles due to the combination of centrifugal force and gravity of a neutron star is the equivalent of an electrical current. But in such case, the current would have an enormous magnitude and it will create an electromagnetic field around the ring of the charged particles traveling at colossal speeds. The magnetic field becomes magnified in the center of the neutron star being added up actually from all directions of the cycle or the ring, and it causes an outburst of radiation energy in both upward and downward directions, normal perpendicular to the plate of the ring. But since the pulsar is rotating at a high speed, the beam is rotating with it in many directions like a spinning top, and it is only captured by a telescope when the direction of the beam collides with the Earth. As you see here, this is the ring where the charged particles are traveling at enormous speeds, and they create the electromagnetic field and electromagnetic waves actually that will pulsate and create the outward directed beams upwards and downwards. As you see here, an example or illustration of the beam. You have upward and downward beam. It's like the spinning top. You see the spinning top? How the normal or the perpendicular axis to this spinning top would be changing heading based on in which direction the spinning top is going. When it's bending to the left, the beam itself in pulsar example would be bent to the left. When it's bent to the right, so will the beam follow to the right direction, to the right heading. So it works in the same way. Now, going to the data set itself, so these are the collected data from the telescope, and you see we have the profile mean, profile standard deviation, skewness, kurtosis, DM mean, DM STD dev, okay, whatever these variables are, but they will affect, based on past collection of data and past results, whether a pulsar or whether a detection is actually a pulsar or not. As you see here, when the class is 1, the class is the result. If it's 1, it means that we've actually detected a pulsar. If it's 0, it means that it's not a positive detection, okay? It's a negative result. This is only some cosmic radiation, some cosmic radio waves that are only noise. Now, going to K-NN, which is the algorithm, the machine learning algorithm we're going to use to detect whether specific data pertains to a pulsar or not. So K-NN is a machine learning algorithm or model suitable for classification, meaning we're classifying whether a detection is a pulsar or not. So it's actually a binary result here. For example, classifying whether an object is one type or another. Usually we are dealing with binary results. So dog or cat, true or false. Here in this demonstration, we're gonna predict, just to show you how it works, whether it is gonna rain or not. Now, this prediction will be based on a historical measurement on the days of when it had rained or not. In those days, what was the temperature and the atmospheric pressure. Of course, in real life examples, you would use multiple parameters, not only two, as in our example here, where you only have temperature and atmospheric pressure as our measurement base. In this graph, we notice two markers. The first one, V, in the cyan color, represents the days when it did rain, and the yellow O marker representing the sunny days. Each value on the graph represents a sample or a day of a year when measurements of temperature and air pressure were collected and it did either rain or not rain. Temperature and air pressure represented on both axes. The x-axis and the y-axis are called features. These are the parameters evaluated to predict whether it is going to rain or not rain. Each marker also on the graph is a data collection that will be compared to an actual measurement in an attempt to check if the result would be rain or no rain. Let us say on a certain day we measured the temperature and the air pressure in an attempt to intelligently predict the type of event that will take place, either V or O. As you see in the graph, X is closer to the no-rain samples. X is the specimen here, having values respectively of 32 for temperature and 60% for air pressure, and X is located closer to the non-rain samples. And this is how K-NN works, by looking at the majority of historical results that are the closest to X. Speaking about K-NN, this type of algorithm is called a classification algorithm, given that it classifies a result into a finite number of categories, in our case either V or O, rain or no rain. This is how K-NN works. The most important parameter probably in the K-NN algorithm is the number of neighbors, or how many vectors we're going to trace outward from X to the neighboring results. We've chosen as an example the number of neighbors equal 5. So the algorithm starts seeking points from the closest to X to the farthest until it reaches 5 vectors, 5 hit points, as you see or as you notice in this graph. you can actually imagine this concept as a ranging process. So X starts to draw circles from the inside out. We can see that in the first circle closest to X, we have 2 hits of O marker. In the second, we have another 2 hits, which are also of type O or no rain. And finally, in the farthest one, in the third circle, which is the largest, it has 1 hit that is V, unlike the others, or rain marker. So the majority of neighbors in such case are O, given that we only have 1 V neighbor, 1 rain neighbor. In such case, X would be deemed as a non-rainy day, given the majority being no rain. Meanwhile, in this other example, as you notice, X has 3 neighbors of V type and only 1 neighbor that is of O or sunny day type. So based on the majority of results being V, the result of prediction given by K-NearestNeighbor would be a rainy day, because the majority of number of neighbors is 3 hits for V marker. However, we need to point to an important fact that X in this case is very close to the separating threshold between O and V. As you can notice, there's something like a separating line that is very close, or a border between the O results and the V results. So even if X was predicted as a rainy day, there would be a possibility of error and it might not rain given the delicate position of X. Another parameter that affects the margin of error is the number of neighbors. This factor can directly affect the accuracy. The reason is, while a lower number of neighbors would give you a majority of one category, a majority of one type, concentrated at the proximity, let's say, of X, a larger number of neighbors, so when you go further from X, you might hit a majority of another category, giving you a completely different result. So for the closed circles, you might have one type, one category, but for the larger circles, you might have another category crowded in these larger circles. So we need to consider a margin of error, which is an important factor in determining the accuracy of the algorithm. So the number of neighbors, when it's tweaked up or down, it will change and it can affect the accuracy of the K-NearestNeighbor algorithm. Now the data set we're getting that we're gonna work with is from the UC Irvine website, University of California, Irvine. You go to the subject area and you select physics and chemistry. It is somewhere here. I'm gonna post the link for it. That's the Pulsar dataset. I've downloaded it and now we're gonna open it in Google Colab. That's where we're gonna write the program. So you go to Google Colab, you sign in, and you go to File, New Notebook. I have already another notebook opened, so we're gonna rename that one. So let's rename it Pulsar Detection. And I need to upload the Pulsar dataset to the local files of Chrome. So you click on Files to the left, and I'm gonna drag and drop the dataset, and I'm gonna upload the dataset that we've downloaded, which, by the way, I've renamed it for simplicity. It is called HTRU, by the way. Let's go to the dataset itself to check what are the names of the fields that are within the dataset. So you see profile mean, profile std_dev, skewness, kurtosis, dm mean, dm std_dev, dm skewness, dm kurtosis. So basically 8 fields, and the 9th one is the target. Okay, so the other 8 are called features, and the 9th one is the target, meaning the result. If class is 1, it means that we've detected a pulsar. If it's 0, it means that it is not a pulsar. It is just a cosmic radio wave noise. So Let's start importing necessary libraries for the program. Now, how I increase the font size, I've actually zoomed in the entire page. You can do that by either clicking on the options here and zoom, or by holding the Control key and scrolling forward with the mouse wheel. Alright, so import numpy as np, import pandas as pd, because pandas would help us read the CSV file. Now, data frame df equal pd.read CSV, and the name of the file, which is htru.csv. Okay, df.head to check whether the fields are with the data set. Actually, there are no fields, so we need to set the fields inside of the names here, the names field. Okay, so let's create another variable which is called calls, an array that will hold the different field names is equal to what are the fields. So profile mean, profile std-dev, skewness, kurtosis, etc., all the way to class. Let us actually copy them. Profile mean, profile std-dev, dm mean, dm std-dev, dm kurtosis, and finally class. Okay, let's run this cell and import next to the htru.csv names equal calls. df.head to check whether the names of the fields have been applied to the data set. Alright, let's check the shape of the data set. So df.shape to see how many rows and how many columns we have. Of course, we have 9 columns that are the fields, including of course the class, which gives us whether this is a pulsar or not. So 9 columns are the 9 fields that we have within the data set. As for the number of rows is the number of samples that we've taken that are stored within the data set, and we are predicting based on these specimens. Okay, so let's check the number of rows or records that have class equal 1 versus those that have class equal 0. So pulsar positive equal df, df class equal 1, dot shape 0, because I only want the number of rows without the number of columns. Pulsar negative equal df, df class equals 0 dot shape 0, and let's print them next to each other. So print pulsar positive, pulsar negative. And you notice the disproportion between the positive values versus the negative values. So we need to do a resample to pull up the number of positive results of pulsar detection so as to make them almost equal. So we need to perform an upsample. So we need to do an upscaling for the values that have a positive class so as to make them proportionate with those having a negative class. The purpose for that is to make the prediction accurate, because we need that both the positive and negative values should have the same number, okay, the same number of occurrences or the same density of records. To do an upscaling, we need to import from sklearn library.utils import resample. We need to resample the values. Let's at first separate the majority and the minority, meaning we need to separate the rows that have class equal 1 from those that have class equals 0. df pulsar negative equal df class equals 0 df pulsar positive equal df class equal 1. To upscale, so we write df pulsar p resampled equal resample df pulsar p, replace values equal true, number of samples should be equivalent to df pulsar n, or negative samples, df pulsar n dot shape 0, or number of rows, and random state equal 1, 2, 3. Finally, we need to concatenate back the resampled positive values with the negative values into the df frame. So we're gonna overwrite the df frame by concatenate df pulsar negative with df pulsar p resampled. Let's display the value count, so print df class dot value counts. So we've gotten an equivalent number for both class 0 and class 1, which will make the results of prediction more accurate. Okay, now what we need to do, because notice something, if we type df.head, the results that are class 0 are on one side and those that are class 1 are on the other side. We need to shuffle them back so as to create a random occurrence of different values. In order to do that, I need to import from sklearn .utils import shuffle df equal shuffle df random state equal 42. Let's display df.head again, and the classes have been shuffled. Okay, they have been mixed up. Now let's try to plot the histogram so as to try to detect a relationship between different features, and by features we are referring to the different parameters here, and the class itself. Let's try to find a specific relationship between these features and the class. So let's import matplotlib.pyplot splt plot.figure fig size equal 8.6, and we're gonna go into a for loop to visualize and try to discern a relationship between different features and the class. Okay, so for I in range 8, because we want everything except the class itself, plt.subplot 3 because we have 8 subplots, plt.scatter df calls of I df class equals 0. So every time class is equal to 0, I want to plot the graph df class equals 0. That would be the x-axis. Let's go to the next line, label equal no pulsar or negative value, plt.scatter df calls of I for the results where df class is equal to 1. df class is equal to 1, label equal to Pulsar, an actual detection. plt.y label class plot.x label calls of I, meaning the name of the field. Finally, present to me the legend and plot.show. And here we are visualizing whether there is a difference between pulsar and no pulsar when it comes to the skewness, the MSTD-dev, etc. Actually, we don't discern such a difference between these, okay? It's not discernible using that plot, okay? But what we're gonna do anyway is working with K-NearestNeighbor right now. So from sklearn.preprocessing import, at first I need a standard scaler to scale the values, okay, to normalize the values, because you have, let's say, values 500, 1000 and 1, okay? We cannot test using these values. We need to scale them, and there are multiple methods. Let's say you get the average of those values, and for each specimen, for each value, you measure it based on how much far or close it is from the average, okay? It's like the logarithm. You're normalizing the value so as to make them a usable value. Also, I need from sklearn.model selection import train test split from sklearn train test split, because we're gonna divide all the records into a training record where we're gonna train our machine learning algorithm, test just to test the accuracy, and split. We're gonna split these records from sklearn.neighbors import K-Neighbors classifier, K-NearestNeighbor. Finally, from sklearn.metrics import, I need to import the accuracy score, classification report, mean, squared error, scaler equal standard scaler. At first, let's split between x and y, x being the features, okay? The matrix for the features is x. So x equal df, the data frame, df.cons, and I want to take everything except the last column, which is what? Which is the class. The class is actually the target. X is the features alone. Now Y is the result or the target. So Y equal df dot columns minus 1, which is the last column. So if I print Y, let's at first run it. If I print Y, you're gonna see ones and zeros. Why? Because it's simply the class. If I print Y, you see Y is the class. Okay. So X equal scalar dot fit transform dfx and Y is df class, okay, or dfy. Let's divide into train and test. So X train, X test, Y train, Y test is equal to train test split X, which is the features matrix, Y test size equals 0.2, meaning 20% are only for the test. They won't go into the pool where we're gonna train our learning machine. And random state equal 42. Let's run it. Okay. So let's create the model. The prediction model is equal K-neighbors classifier number of neighbors equal to 5. Model dot fit X train, Y train, and finally Y prediction, which is a new variable, equal model dot predict X test. Finally, we'll print the classification report Y test and Y prediction, meaning it will measure the accuracy, how much of what has been tested by the algorithm is actually the predicted value. So it will compare both to get us the accuracy of the model. And you have the accuracy 98%. So to give you an example, let's create a new array. Let's say X sample equal, and we'll get one of the rows of the data frame, but we will tweak them. So here the value is 0. Okay. Let us copy. We're gonna change the values a little bit, 4 instead of 3, and we're tampering with the values a little bit. And let's try to predict the actual class for this new sample. So Y and pred Y new prediction equal model dot predict X sample. Alright, and you have the result of this prediction is 0, meaning it's not a pulsar. Actually, we can a little bit change or enhance the result by writing this condition. So if Y and pred is equal to 0, print no pulsar, else print pulsar, and let's also print the Y pred as well. Okay, so Y print YM pred. And the result is no pulsar. Okay, thank you for watching. I hope you enjoyed this training.